Good day. I'm Amira Belle Reyes from the Department of EECE. I am going to discuss the concepts used in creating our project, which is the microcontroller controlled rope elevator. As the name implies, our project is designed after a rope elevator. So, what is a rope elevator? A roped elevator is the most popular elevator design. In this design, the car is raised and lowered by attraction steel ropes rather than pushed from below. The design of a roped elevator is the ropes are attached to the elevator car and looped around a sheave. A sheave is just a pulley with the grooves around the circumference. The sheave grips the hoist ropes, so when you rotate the sheave, the ropes move too. The sheave is connected to an electric motor. When the motor turns counterclockwise, the sheave raises the elevator, and when the motor turns clockwise, the sheave lowers the elevator. So, what are the relationship of this project on strength of materials? First, the cables attached to the car experiences both stress and strain. In this case, the stress experienced is tensile stress, since the force applied by the motor is pulling the car. The cable also experiences strain. As defined, strain is the ratio of the change in length caused by the applied force to the original length. In creating an elevator, it is important to consider the properties of the cable to be used to avoid deformation. The cable should be able to support the car when it is loaded. Second relationship is the sheave, which is connected to the motor, experiences torsion. As defined, torsion is the twisting of an object due to an applied torque. When the motor rotates the sheave connected to it, it will experience torque. Therefore, the torque caused by the motor should be considered to avoid the twisting of the sheave. Thank you.
Now that you guys learned the concept behind how the elevator works, you will now witness the actual demonstration of our project, the microcontroller controlled rope elevator. In the demonstration, you can see how the elevator car goes up from the first floor to second floor, from second floor to third floor, and how it goes down from third floor to second floor, and from second floor to first floor. Now here's our demonstration.
Good day. My name is Rhemylle P. BAUTISTA, and I'm here to present to you our computation for the project called Microcontroller Controlled Elevator. So first, we're gonna solve for the tension. Our design is like this. So we're gonna have tension right here. And for the material we use, which is the nylon string, the stress allowable for that certain material is 45 megapascal. So we all know that stress is equals to force over area. We already know the stress, which is 45 MPa. Then we also know the area of the string, which is around 1 millimeter for its diameter. So diameter is equals to 1 mm. So area is equals to pi over 4 times 1 mm squared. So we're gonna find the maximum or the tolerable force that is allowed for the weight of this car. So the force allowable is equals to 35.34 newtons. So for safety, we're gonna use 30 newtons. So there's torsion around here. So first we're gonna solve for the Tmax, then the angle of twist. For the torque of the motor, there is a motor here. It is equals to force times the perpendicular distance. So we're just gonna assume that the force is 30 and the weight of the cart, allowable weight. So 30 and times the length of the string, which is around presumably 355.6 mm. This is equivalent to 10.668 kilonewtons per meter, or 10.668 newtons per millimeter. For Tmax, equals to 16 times 10.668 newtons per millimeter all over pi times 2 mm squared. So Tmax is equals to almost 6.79 kPa. For the angle of twist, this equals to TL over JG, which is equivalent to 10.668 times 10 millimeters, which is the length. Pi over 32, the length of this rod, the rod of the motor, 2 raised to 4 times 100 times 10 raised to 3. This is the shear modulus of the steel, which is the material of the motor. So the angle of twist is equals to 0.68 degrees.